Morning, everybody. I'm going to give it a few minutes for some more people to gather from the previous talk, and then we'll get started. I'll probably give it till 9:35, give it 5 minutes.
Yeah, I was going to say, since this can be an interactive session, folks are welcome to say hi with their cameras if they want to. You don't have to.
You can wave and do whatever you wish. Mm-hmm.
There were requests to see your cat, Rebecca, at some point.
Right, that happened on the first day, yes, because she was being whenever she hears my voice, she thinks that she should be getting attention. And so she was being extremely vocal during the last part of one of the sessions. And I did try to show her very briefly, but people were leaving. So I've closed the door right now because she was trying to ask for attention. It's starting now, Chris. We're just waiting 5 minutes for people to join from the previous talk. So we're going to start discussing everything at 9:35 because I just want to give people a chance to, have a bio break between the talks that have just finished in this session now. So you're in the right place. Don't worry.
I don't think he's on the Zoom, so I just typed.
Oh, okay. Apologies.
You're responding to his Slack message.
I am, yes. Yeah, I might bring the cat in later. For now, she's outside because she keeps on jumping on me when I'm talking.
Oh, I guess Jen announced it and reversed the times. She was saying the study one is now, and wait.
See. I know that our one is now. Maybe because I believe that they're being set up at the next one. Maybe we should make a statement in general.
Yeah. What? Yeah, the schedule says it's now.
Yeah, and Ryan said it's now.
Yeah.
Yeah, at 10:30, I'll actually be jumping right from this one to the other room for the SETI session. I have that scheduled for 10:30 to 11:30.
Okay, thanks.
I think people just got a bit confused.
And I can't type. Okay. You could probably get rolling in a second here.
And for everybody online, good morning. Hello, my name is Rebecca Hounsell. I'm going to be leading this sprinter session today. And I have my colleagues online as well, Nicole and Tom Barkley and potentially Gert. This is going to be run more as an open session, so you can take yourselves off mute. You can raise your hand to ask questions. We really want this session, which is going to be discussing Lightkurve and different tools available for the analysis of test data, to be very much open and free-form. So if you have particular objects of interest, or if you're having particular problems in Lightkurve, what I suggest is you can raise your hand using the interface here. So let's see if I can do this myself. And then I can answer your questions, and then you can lower your hand, or you can type your questions into the Slack channel. I believe we have a dedicated one, which is the TESS GI Lightkurve. And we will, Nicole has very kindly agreed to help moderate these questions, and I can help to address them for you. So I think it's now 9:35, so we're going to get started. So the first thing I want to ask, and I know there's quite a lot of people here, it's currently at 70 participants, and so it might be difficult to ask this online, but I have several tutorials which have been listed all on our TESS GI webpage. So if you look at the Slack channel, At the top, there are some bookmarks. The first one, which will take you to the tutorials page, and that will list, if you click on it, maybe I should show you my screen here. So this is the, this is the TESS GI page, Lightkurve page. This first link here will take you to the tutorials, which we're going to be looking at a bit today. And that's given here. So you can click on each one of these and you can download each one here as well. And then we have, this is just a link purely to Lightkurve, which will talk to you about the package itself. And there are various tutorials, which you can find here. And then this is the Zoom link. So those of you who've made it here have obviously found that. So I won't go over that part of it for you. Okay, so now getting back to what we're going to be talking about today. So, okay, maybe by show of hands, if you can do this. Who here is new to Lightkurve and has never really used it very much before, and would really like to have a good understanding of, you know, how to extract Lightkurves from test data? For those of you on the line, if this what I just said applies to you, how about you raise your hands on the screen? Let's see. Just give you a moment here.
10 so far.
10 so far. Let's give it another minute or so for those of you who might be needing to find the raise hand button.
More than 10. And you can find that, yeah, under reactions, raise hand.
Okay, so we have, yeah, 3, 6, like maybe like a dozen or so. Okay, thank you very much. If you could put your hands, lower your hands for me now. Okay, and so now those of you who are a bit more experienced with Lightkurve and haven't really used the corrector class yet, so those of you who want to know how to do something a little bit more detailed, how to remove noise and scattered light from your Lightkurves, those of you who are interested in learning about that, could you please raise your hands?
A lot.
Okay.
Yeah.
I think I know which direction we're going to be going in today. Thank you very much for doing that for me. It just gave me a good understanding of where I should be focusing this tutorial. For those 10 of you who previously stated that they haven't really used Lightkurve beforehand, you will have my if you go to the tutorials page, which I showed you earlier, you will find this specific tutorial that is an introduction to Lightkurve, and it will walk through the process of how to extract Lightkurve files, which are products that are available with TESS. It'll also teach you how to extract a Lightkurve from target pixel files and FFI data, and it will really just go through that procedure with you here. So I'll very briefly just show you here the learning goals of this tutorials, which is open test data products, how to use Lightkurve to access the various data products, and how to analyze and assess your data. And as you can see, I give a very nice overview about the TESS. Oh, yes.
Sorry, your screen is scrolling strangely for me. I'm not sure if anyone else is seeing that.
How does it look right now?
It's very choppy. Maybe try going to a different tab and then back.
Okay.
Like it's not
this better?
Scrolling. Does anyone else see that issue?
I have the same issue, yeah.
Yeah, the same issue. Okay. Yeah, so
okay.
Like only a part of the screen is scrolling. It's very funky.
Why don't I move my previous tab? I'll delete this one maybe.
Yeah, or stop and start share again. Maybe.
Yeah, why don't I try that? Thank you very much. Please, guys, jump in and let me know if you have problems like this. Okay.
But all the tutorials, yeah, are on the website as well, so you can follow along there. Yeah.
Okay, I've now reshared my screen and I'm going to scroll again. How does this look?
Much better.
Ah, perfect. Thank you very much, guys. Okay, so yes, this tutorial will just cover some basic things about what TESS is, the MAST, so where you can get products from MAST, and then it will go into how to access the data products using the Lightkurve package. And as you can see here, shows the different outputs and things you get. and obviously the different light curves and things you can get. So given the number of people who are more interested in
Rebecca,
using...
I think that scrolling issue is happening again.
Sorry.
Oh,
yeah.
my goodness. Okay, well, I will stop sharing.
Is there a way to like...
Can you scroll down the notebook or the website rather than the notebook? Were you on the notebook page?
Yes, I'm on the notebook. I can go to the website and potentially do that if that might make it easier. Let me try that.
It'll be less interactive, but like the HTML,
Okay.
not the Jupyter notebook. Right.
How is this? This is the HTML page.
Yeah, that's not working either.
Okay.
Rebecca,
Okay.
I would suggest restarting your share, but share Safari only, not your full desktop, and see if that helps.
Sorry about the technical issues here, guys.
Lightkurve works better than Safari.
It does. Okay, I'm sharing my specific noise removal Jupyter notebook. How does this look?
Try scrolling.
How are we doing?
I think that's working. Yeah, I was giving it a minute.
So far,
Okay.
so good.
Okay.
All
good.
right. Thank you very much, everyone. Okay, so let's get cracking then. So again, if you have questions, please interrupt. This is meant to be interactive and a discussion with you all. If there are too many people talking at the time, obviously raise your hand and I'll answer questions. And I'm going to rely on Nicole to make sure that I'm seeing those questions. Again, also please use the chat as well, and we'll do our best to address all your issues. So, hi, I'm Rebecca, for those of you who don't know me. I work in the NASA Goddard Guest Investigator Office with all of my collaborators here. And so for this tutorial, given what was indicated earlier, we're going to be focusing on teaching you, the user, how to remove scattered light and noise from a TESS Lightkurve. Now, this will work best if you've downloaded a copy of this notebook for yourself. It's a Jupyter notebook. For those of you who might not have ever used Jupyter notebooks before, or haven't used Lightkurve before, like some of you indicated, you can actually open this if you have a Google account as part of the Google Colab, and you can actually run and install everything through there. And you just need to make sure that you have this command at the top of your Colab notebook in Google. So yeah, this notebook is essentially going to focus on how to access the various data products for TESS. So it does give you a brief overview of that. And then, as I say, how to account for instrumental effects and scattered light and noise, etc., via these new corrector classes that have been developed. So the first thing that we do is we do the standard import of Lightkurve. And then I'm going to give you a brief introduction to the corrector class. Now, as many of you have probably seen in all of your work, TESS Lightkurves are wonderful, but they can have some systematic trends which are caused by noise or other sources of noise, like scattered lights and instrumental effects. And only the Lightkurve objects, so these are the products, the spot products, which have been fully processed, and these have had these effects that have been removed. So data which is derived either from target pixel files or from full-framed images, they typically need to go and have some further processing applied to them to make the data scientifically usable. And that can be tricky to figure out how to remove these sources of noise. So to aid the user, the people who have worked on the Lightkurve package have kind of developed this corrector class of tools, essentially. And for each one of these things, when I'm describing it, you can click on these links, and it will give you an introduction to these different classes in Jupyter in Lightkurve. So I hope you find that useful. Okay, so I'm going to give a very brief overview about each one of these because there are a fair few. So the first one is the co-trending basis vectors. And these are generated from the most common systematic trends observed over the entire sector. So remember, TESS observes in these big sectors, and each sector is observed for about 27-ish days. And each TESS CCD and camera has its own CBV. And there are 3 basic types of CBVs, which we consider. There are the single scale, multi-scale, and spike. The single scale, if you want to ever use this contains all the different systematic trends, and they combined in a single set of bias vectors. And essentially, the CBV performs better. This type of CBV performs better at preserving the longer period signals. So maybe not so useful if you want to look at shorter period things. And then you can use the other ones which are mentioned here, like the multi-scale or spike. And I've written down a brief overview of what each one of these do, so you can read at your leisure. So, you know, the multi-scale contains systematic trends in specific wavelength-based band passes. And, you know, these are better when the periods are closer to the transiting planet durations, etc., etc. And then there's the spike, and these ones are better for removing short, impulsive systematic signals. Okay, so that's the CBVs. The next one is the regression corrector, and the regression corrector was originally part of Lightkurve version 1, and now it's just been, you know, it's still part of Lightkurve 2. And here the Lightkurve is detrended against vectors that we think are predictive of the systematic noise. So for FFI data, we basically select and define an aperture for object of interest, and then the pixels outside of that aperture, they're going to be used to create the vectors that are predictive of the noise, and they get removed from your object signal essentially. And then PLD correctors, these are pixel level decorrelation. This works by identifying a set of trends in the pixels surrounding the target stars and performs a linear regression. So it's very similar to the one I mentioned previously, but it's a little bit more easy to use. So these are the 3 that I'm going to focus on today. I'm going to go through a specific case. I believe I'm using KT Eri, which is ANOVA, and I'm going to apply each one of these different correctors to KT Eri and see what the data looks like, and show you the user how you can vary some different parameters to get a better understanding of what's going on. Do I have any questions so far? Please, I know I'm going pretty fast, so please feel free to interrupt, and I'll just give you a moment now if you want to ask some questions.
I don't see anything in the Slack yet, but people are also welcome to raise their hands here and unmute.
Nope, okay. I'm just going to zoom ahead then. Okay, so this part here might be useful for those of you who are first-time users. So how to use Lightkurve to access the various data products and create a time series. So essentially, there are 3 ways in which you can obtain the various data products. You can look for your object in a full frame image, so that's that sector of the sky. And you can do that using this function called search test cut. And again, for those first time users, you can click on the links here, and it will take you to the Lightkurve page, which will give you a good description of how to use that function and what your inputs need to be. Okay. The next thing is you can look for target pixel files using search target pixel file. And then, or you can look for light curves that have actually already been produced for your object using search Lightkurve. So as I say, for the purposes of this tutorial, I'm going to be examining KT Eri, which is a bright nova that went off in about 2009. So we're not going to see the eruption event, but we're going to be looking at it in quiescence, which is also useful for this tutorial because it's not such a big signal, and we can really see how noise is affecting it. So to test our various methods of noise removal, we're looking at this object, and we're going to be looking at the full frame image data. So we're going to be using this to download and search for our data, essentially. So the first thing I'm doing is doing this search test cut. And then for your first time users, when you put in something like this, so you're putting in what function you want to use, you're putting in the name of your object, and what will happen is a table will be returned, and that table will tell you, what the sector was, what year it was taken, who the author is. On each one of these as well, there's a hyperlink which you can click, and then it will give you more information about that author and where the data comes from, what the exposure time was, the target name, and the distance to your object. And this is useful if you're doing like a radial cone search, so you can figure out how far away from your actual specified RA and DEC. Okay, So essentially we see that this is observed twice, once in sector 5 and once in sector 32. And we're going to look at sector 32 and we're going to download the data from that. So to do that, we're specifying the second part in the array. And this, again, just for the first time users going over this briefly. And we're going to do quite a large cutout size here because we really want to, as I said previously, a lot of our way in which we remove the noise relies on the pixels outside our object of interest, and we want to make sure we're getting a good sample size there. So I'm doing a much larger cutout size than people might typically do. So I'm going to go through here, and this is going to download the data, and this is going to display it. So great. So our object is this really faint thing here. And as I said, this is an object that isn't an outburst, which is why it's so faint. Okay, so the next thing we're going to do is we're going to create our light curve based on this full framed image. And like I said, our object was the thing in the middle. So for those of you, again, who don't know how to do this, what you can do is you can create a little Boolean array, which kind of goes over the pixels that you want for your object of interest. It makes up an aperture, which you define and use later to create your light curve. So I'm just going to run through this quickly. And then I'm going to use Lightkurve's built-in function to Lightkurve and specify the aperture mask that we want. So I'm going to use, aperture new instead of threshold. And then we're going to create the light curve. Okay, so that's now our light curve. And we can see that there are these massive spikes. And obviously that's not from our object. That's actually due to scattered light. And we can also see that, again, for the first time users, we can do this thing called interact. So we can download our object and do, let's see if this runs. Okay, so this is showing our FFI. And this allows you to just go along and see what the data look like. And you can see there's this big spike here. And this is caused by scattered light. So this is obviously not our object or anything like that, but this thing is caused by scattered light, essentially. So what we want to do, like I said, is we're going to go through each one of these different corrector classes that I previously talked about. And we're going to apply each one to our data and then examine it and compare it and see what it looks like. So the first thing that we're going to do is use the CBV. And to do this, we're going to have to first import the CBV corrector from the Lightkurve corrector class and then refer to our previously generated light curve. So let's run through here. Okay, and this tells you that there are 5 sets of CBVs, all associated with sector 32, camera 2, CCD4. And Rebecca. I just saw a question.
Yes. You see.
Yeah, I do. So hello, Steve. Yes, there are different quick ways for defining apertures. You can use things where there's a threshold tool, which can do it based on a certain sigma from the background. There's also, depending on if you have a target pixel file, the TPF optimal aperture, which is just defined as aperture mask, I believe, or pipeline mask. And there's also, if you're referring to this Boolean type of thing, I mean, this is kind of one of the quickest ways of doing it, which is basically just copying the shape of your object and then specifying which parts in the array you want to be true. I actually have a tutorial which discusses aperture photometry. You can find, and I will post in the link here.
I can find it if you want.
Oh, perfect, yes, which actually talks about doing aperture photometry, and Nicole will post that for you. And a great question, thank you very much. Okay, so going back to here, this is saying, yes, there are 5 sets of CBVs in sector 32, camera 2, CCD4. And the number of CBVs per type is also given. So we're going to plot this up. Okay, so we can see this is 1 through 8, and 1 through 8 are typically what are used because using anything higher than this can actually sometimes introduce noise and issues. So we need to be careful about which ones here we're actually using. And we also need to think about what kind of CBV we want to apply, since we don't want to overfit things, and we don't maybe want to consider all the different types of systematics. We want to make sure that, you know, this is an object in quiescence, so there's going to be some different kinds of variability. So we're going to use this multi-scale and spike options that we discussed earlier. And so we can specify that using this array here. And then we, like I said previously, we only want to use the 8 CBVs when we're using the single scale function, and then maybe all the spike CBVs. So we can again specify that using this array here. Okay, so next we want to check that basically the vectors that we're going to apply here aren't going to over or under fit our data. And there's a nice little handy way of doing that. And I'm just seeing, apologies, a question in the chat. It looks like mass might be a hard time delivering products right now. Oh no, I'm so sorry, everybody. Okay. And Emily, were you just using specifically KT area, or did you put another object of interest in there for yourself?
I was just looking at KT area. I am not using your notebook, but I'm using all the same things in just a regular Python script. So I'm curious to see if anybody who is not using the notebook is having the same problem as I am.
Also, I have the files already downloaded onto my computer because they get stored in the Lightkurve cache. So that's the other thing, that if you're trying to access and get new information, you might not be able to, whereas I have it already stored. So yeah, if anybody else is having that issue, please let us know.
I know they do tend to have problems when a lot of people are looking at the same data at once and trying to download it.
Okay.
I think I had this problem using the notebook, but it's fixed now. I mean, my data went through, so I'm good now.
Okay. Okay. Well, I'm hoping it will start working again. I apologize. Maybe keep trying. It sounds like, you know, if people, it takes a little bit of a while, and maybe it might be overloading the database, as Stephanie says. So maybe give it a minute and hopefully we can progress onwards. Okay, so I'm just getting back to this. So this is a way of which you can essentially check to see how well you've done your fit, whether it's over or under fitting. This takes a little minute to run. But this is a really useful thing, because essentially when you want to look at this plot, you want to make sure that, you know, you want things to be around about a goodness metric of about 0.8. You don't want it to be too under or too over. So just take a second here and hopefully it will come with this plot. And how people, oh, sorry.
Oh, sorry. I was going to say, while that's loading, did you see Eric Jensen's question?
Oh, yes. Hello, Eric. So sometimes when you explore the CBVs, you found cases where it doesn't find any CBV for a given field. Is that normal occurrence, or I'm not sure about that. If it's for specific objects, you could put it in the SAC and I could try and see if I can play around with it later and maybe figure this out for you. I haven't found that personally. I don't know whether anybody else online has.
Yeah, that seems like, I wonder if it's an edge case where.
It might be an edge case situation, yeah. But I'd be very interested in trying to play around with that and helping you figure that out. So please send me a message about your specific case and I'll have a look at that today. Okay, so as you can see here, I've essentially chosen a certain value that I know will bring us around about to 0.8. So what I've done here, so I've checked to try and make sure that I'm not over or under fitting, is use the value that I've input here and apply that to my data. So, and I do that using my alpha value defined here. Okay, so I've kind of gone out of my field of view, so I can change these parameters to see what it looks like, or maybe get rid of them. So this is really useful because it essentially shows you how well or how much you're removing your data or not. And like, it's a useful diagnostic plot that you can apply here. And so my final plot looks something like this. And as you can see, it's removed a lot of the large scattered light. There's still some residual here, and it's also removed a little bit of the slope, but not a huge amount. So there's still some sloping issues that we're seeing here. So this isn't perfect. And again, you can keep playing around with the CBV corrector and maybe, you know, changing your alpha amount and, you know, maybe changing which type of CBV you're applying to adjust this further. But for now, we're just going to move on to our next case. So, okay. So again, we're going to go on to regression correctors. And this method relies on looking at pixels outside of the previously defined object aperture to determine our systematics. So we can apply the regression correction as follows. So you need to import this regression corrector and this design matrix. Okay. And then next, we're going to define this design matrix. And this design matrix contains all the systematics detected in the pixels outside of our aperture. And actually, I'm going to pause for a second and ask before I just rush on into this. Are there any more questions about CBV and the correction regarding that? If not, okay, great. I will charge ahead then. Okay. So we've defined this design matrix, and that's going to contain all the systematics detected in the pixels outside of our object aperture. So we've run through that. And now we only want the most dominant vectors. So we're going to specify the number of principal components as follows. So, okay, we're going to say 10, which is ridiculous. And I'm doing this just to illustrate a point to show you what this looks like. Okay. So we can see all these things here, and we can see there's some big changes here. Maybe not much going on up here. So we don't need 10. That's a huge overkill of everything and not accurate at all. So from this, you can see that 10, specifying this PCAs, is completely excessive. We should not use this. We should probably maybe just use like the first 5 or so where we see this variation. So we're now going to switch it and basically say, change our value, please, to 5.
Could you just say, sorry, could you say a few more words about what criteria you're using to pick 5 of those? It's just where you see sort of discontinuities there? Right.
So essentially what you're doing is you're trying to use the background pixels to figure out, yeah, this variation, these spikes, these discontinuities, as you're saying. And so if you say, okay, well, we're going to use these 10 principal components, that's obviously not accurate, and you're probably in these last ones just essentially, yeah, overfitting or introducing noise or doing something like that. And so you don't necessarily want to be doing that. You only really want to consider the ones which actually seem like there's this variation going on. Does that help to answer your question?
Yes, thank you.
Okay, no worries. And then Michael, you have a question. Is there any quantitative metric for overfitting? So what I've done in the past when I've looked at these things is essentially do this goodness, the plot that I showed you beforehand, which is looking at this goodness metric. And there's actually, and you can use this on, I believe you can use this on other things as well. And there's actually a tutorial about that on the Lightkurve page, which talks a bit more about over and under fitting. And so maybe I can send you that specifically later. You can use regression corrector for Lightkurves from FFIs, yes, Emily. And that's actually what I'm using the data on. All of this is based on data has been extracted from an FFI. It's not from a Lightkurve.
But can you use it the other way around for ones that are from the existing Lightkurve instead of for the FFIs, or does it not contain this information about the surrounding pixels?
So on Lightkurve files specifically, that is just an actual process time series. So there isn't the information on the surrounding pixels. But what you could do is you could use the target pixel file that's produced for it, or but that was basically from that Lightkurve, and use the data from that. But a Lightkurve, if you already have a Lightkurve file that's been produced by the Spock, a lot of the noise and the scattered light and everything will have already been removed from that, so it's not really necessary. Does that make sense?
If you wanted to reprocess it yourself, if you wanted to, the existing one isn't removing the noise satisfactorily, you would have to re-extract it from the full frame.
You could use the target pixel file. So if there's a Lightkurve file, there's a target pixel file for that. So yes, you could use that information. And then that would give you the same cadence and everything else that you want, whereas an FFI wouldn't.
Thanks.
Let's see. Okay, so just going back to this. So yeah, I'm only going to pick the first 5, and then I can show you this plot here. And please, by the way, if I've said anything inaccurate, my other colleagues on the line, please correct me. Okay, so the Lightkurve regression corrector, as I said earlier, uses linear algebra to find the combination of vectors that make the input Lightkurve closest to 0. We therefore need to add one more component, which is an offset term, to be able to fit the mean level of the Lightkurve. And we can do this by adding in this appending constant into the design matrix. So this is this thing that's shown here. Okay, so then we now pass this design matrix to the regression corrector, and then that does the detrending for us. And then we can have a look, and we again can use this really useful diagnose, which is part of the corrector class, to see what this looks like. And this will be a bit better, I think, shown here. Okay. Okay, maybe not. Okay, so here I'm going to zoom in a little bit here just so you can see a bit better what's going on, but you can again see that this peak here has been removed. Okay. Okay. So you can see there's the original, which is given in the gray, and then there's a regressor. I'm sorry if you can't see my screen very well, but I'm hoping you have the notebook and you can play with this yourself. So this is the regressor, and then you have the original in gray, the corrected, which is here, and any outlier or cadence mass would have been shown in red or blue. Okay, however, the regression corrector assumes that you want to remove the trend and set the Lightkurve to the mean level. And for TESS scattered light, this isn't exactly true. So the TESS FFI Lightkurves have this additive background to them. And as such, you don't necessarily want to reduce the flux to the lowest recorded level. You want to reduce the level, to the lowest recorded level. So to do this, we can look at the model of the background that the regressor corrector built up. So it will have something here. And you can essentially apply that. And so the model should never go below 0, essentially. You don't want to over subtract your background. So we can do this using the following code. Okay, so this is now our corrected KT-ERI Lightkurve. This seems to have done a really good job at removing the scattered light that was shown here, and also removal of some of that slope that we were seeing earlier. So this seems to have done a pretty decent job. And again, there's other things that you can vary here. So if you go to the web page that describes the regressor corrector, it gives you different parameters you can input. But you can, again, mess around with like the number of principal components, mess around with what you're appending, all those sorts of things to try and improve the removal of noise from your Lightkurve. Okay, so the next one I'm going to discuss very briefly is this PLD corrector. So this is built on top of the regression corrector. And actually, again, I'm going to pause just in case there are any questions before we move on, specifically about regression correctors.
May I just ask, you were talking about removing the background, so you were dropping the flux down. But in that plot we just see above, the flux is still hovering around, 1,000. Like, what type of level should we be looking at here?
So you're asking what the background estimate should be for your object, is that correct?
Yeah, like I guess how did we get to this particular sort of baseline of about 1,000? Right,
so essentially, okay, you can actually play around with this tool which is called, I think it's background estimate, which will give you an estimate of exactly what the background should be. The one that was removed slightly from here was part of the background model that was calculated as part of the regression corrector. But if you're asking, so essentially, let's see if I can find it for you. Okay. Yes, you can do this thing here, which is called estimate background. Have you ever tried this?
No, not personally, but thank you.
Okay, So this is something that I've been playing around with recently when I've been looking at FFI data, and essentially even when I have a corrected Lightkurve, I still have this background that's in there. So with test data, there's kind of this additive background, and you want to remove that a bit, but there's still this baseline background that you essentially want to remove. And so to do that, I've been using this estimate background to give me a value. It basically produces a Lightkurve. And then I've been taking this, and I have personally been taking like the median of that and removing that from my data, which I find particularly useful. So there's different things you can play around with. I would suggest looking into this. I don't know if any of my colleagues have a better answer online.
Can I ask just a quick sort of meta question here? This is listed as being part of the Kepler target pixel file class, but then the description mentions both TESS and Kepler.
Yeah.
Is it generally okay to use things from that are listed under the Kepler class on the TESS pixel files, or not? How can you tell what works?
I think there's a TESS version of this, but they can kind of be mixed. So there is actually no, there isn't. It's a good question. In my experience, when I've been doing this, they seem to be pretty interchangeable. I imagine there are some very specific cases, though, where it's more suited for something Kepler related. And therefore, when you're doing those sorts of things, I would advise reading the documentation, like, for instance, for this and seeing what it's really doing and thinking about whether it's applicable to your data. But in my experience of what I've been doing, they do seem to be pretty interchangeable. Again, if Gert's online, maybe he can give you a better answer, or somebody that's previously worked a lot more with Kepler data. But for these specific tasks, they seem to be pretty interchangeable.
Okay, thank you.
Very welcome. So, Eric, did I answer all of your questions that are here?
In the Slack, you mean?
Yes, in the Slack. Yeah. I'm going to assume yes then and move on. And then Michael also made a very good point in the Slack as well with respect to the question about baseline flux. It may be worth basically that the answer depends a little bit on the magnitude of the object as well. And thank you very much, Michael. Okay, if that's it, I will move on talking more about the PLD corrector, which is kind of very, very similar to regression correction in the way that it works here. So this works by identifying a set of trends in the background pixels, so what we talked about beforehand, surrounding the target star, and performing this linear regression to create a combination of these trends that effectively model the noise. The noise model is then subtracted from the uncorrected Lightkurve, and the difference between the PLD and regression corrector is that the regression corrector asks the user to define pixels, whereas the PLD corrector doesn't necessarily. However, you can define an aperture inside of it if you want to. And again, I would suggest looking at the API for Lightkurve for this specific corrector class and just playing around with the different parameters that you can input. But for now, what I will do is this. And this is essentially, you're inputting your PLD corrector. You're just specifying essentially the cutout that you made earlier. Again, you might want to just, for the consistency, I'm saying the number of PCA components is 5. And then I'm just running through here. And it will take a moment. Okay, so this is just showing what's happening here. Again, I want to play around with the axes a little bit. So just going to play around here. Okay, so you can see the uncorrected, the corrected, which is kind of in this gray here, the spline, and the background. Okay, so now we can also, one thing that I think is quite useful to understand how this works is to look at the apertures that are being used to perform this correction. So for TESS, the dominant source of noise is the scattered light. So by default, only want those pixels, the background to be used. And in the third panel, we can see that, this background that's being defined doesn't include our object, and also doesn't include, you know, the bright stars as well, because obviously we don't want that to be included in our calculations. So this is kind of a useful thing to look at, to do a sanity check of making sure, you know, where's my object being defined, what's my background being defined as, so you can try and understand what's actually happening. So this is something you can do by just specifying diagnose masks. Okay, so we have a question from Alison. How's the different corrections impact the error bars from TESS tend to be reported in count? So how should errors be handled when we're taking out background noise from our flux? It's a good question. It's a very good question. I don't know, Tom, do you maybe want to field that one?
No.
No? Okay. So let's see. Errors from TESS tend to be reported in counts. How should errors be handled when talking about background noise from our flux? I will have to look into that a bit more for you. I apologize that I don't know. It's a very, very, very good question. I don't know the answer off the top of my head, but I can look into this more for you today, Alison, and get back to you if that's okay.
That's fine. Thank you.
Thank you very much. But it's a really good question, so thank you. Okay, so I'm just going to show what the result of this plot is here. So, okay, we can see that the scattered light was removed here, so there isn't the thing, but there is still this slope in our data. So that seems to suggest that we need to play around. So our background wasn't correct, maybe potentially very well modeled, and we need to play around with things a little bit more in this corrector class. And you can do that. There are various input parameters you can mess around with. So we're just going to now compare each one of these corrector classes to each other, because we have seen some differences in the light curve. No one analysis method has been completely perfect. And that's kind of a point that I want to hit upon here. There is a lot of things you need to play around with, and a lot of examination of your data to really make sure that you understand what's going on. So here's the comparison that I'm going to do. Okay, so we have the original uncorrected light curve, which is shown in black, if you can see this here. So this is where there's this big scatters light still going on. And it seems like, you know, there has been a pretty good job on several of these of removal of that scattered light. And there's also this slope that we see. And it seems like the regression corrector seems to have done the best at removing that slope in the data as well. And some of the others maybe haven't. And this doesn't mean that those aren't great correctors. It just means that you maybe need to try and understand what's happening in your data a bit more, and playing around with how the background was modeled. So maybe study the background and the slope. So Jonathan, when you're asking that question, when you have that linear slope, what if it's real or not, and how do you differentiate between these? What you might need to actually do is just, you know, look at the different forms of data, look at the background that's being removed in each of the correctors, and seeing if you think it's applicable or not, looking at the goodness matrix and the fit and the overall underfitting. It is really about just trying to understand your data, and playing around with some of the additional parameters that might exist for the different corrector classes. So in summary, there's no necessarily one perfect solution. The result from the regression corrector seems to have removed the most scattered light. You may have discovered that removing from noise data is a complex issue, and I feel like this is highlighting that. You should always examine your method of noise removal and inspect all final products. And the tutorials listed below will help you better understand the details of each one of the processes that I've just very, very briefly discussed. And I hope that you found that useful. I'm going to give you some time to ask some more questions, and hopefully I can answer them. But there's also other tutorials which I have I put up online, which is one is understanding crowding. So this is the other factor that might come into some of the noise removal issues here. There's kind of a second stage where you talk about crowding issues. But yeah, I'm just going to leave it open for a minute and allow you to ask questions.
And there's one from John Labarty Bartz in the chat.
Yes. So this is to do with the downwards linear slope and how do you differentiate. Again, this is kind of going into the next part of the data where you potentially may need to understand crowding, how much light was missed from your aperture that you defined, and how much light was maybe included from other stars. Also trying to understand the shape of the PRF. The reason why I believe that this why the downward scatter isn't necessarily real either is because when I compare it to flux from the other sector and also compare it to, they're actually Lightkurve files for this sector, that downward slope isn't there. So I believe that this is some sort of non-accurate removal of the background. And so, yeah, this is what I mean. You really have to kind of dig into your data a bit. Of these corrector methods, which one typically performs the best for astroseismology? So again, this really depends on what you want to do. I've seen some very good results with CBV correcting, but again, it is very specific to your object, crowding, and other sorts of issues like that. I don't want to give a one specific answer here. Sorry if that seems like a cop-out, but it's an honest remark. I don't know what your data looks like. If I just downloaded the SAP Lightkurve, how much, if any, of what you discussed today has gone into that? Same question for PDC. Okay, so if it's going to that. So when you mean just download the SAP Lightkurve, you mean as the Lightkurve file? Because the Lightkurve files contain the PDC SAP and the SAP.
Yes, so a Lightkurve file, and I've got both different types of flux values, and just sort of, I've never fully understood what has gone into both, and based on what you've talked about today.
Like what is flux doing, right?
Yeah, so essentially, and there are people who are on this call who might be better, so Michael, to address this there is background removal, there is crowding correction, there is optical aperture flux that's outside of the aperture that's been defined. There's a correction for that. There's bias corrections. There's all those sorts of things. And if you're talking about maybe what might be closest, and I feel like this might be the closest answer is the CBV kind of correcting, because I know that there's they use the CBV within that. So and also this is written down in I believe the data products handbook, where they give descriptions of each one of these and what processes might have been done. But I would say there's crowding corrections, flux corrections, background corrections, bias corrections. So quite a lot essentially.
But are you talking about for the PDC, or that's also in the SAP?
So they use their own pipelines for this. So that, so and Michael has just given a good answer here.
Thank you.
Okay, what is the slope is physically related to the change in the object? How do you differentiate between real change and correction needed? That's, as I said, that's a very good question for my object, because I've seen the Lightkurve with the PDC SAP. I know that slope is not physical, and that's kind of difficult for a given object to know the answer to that in what you're doing. It's like I was saying, you need to just try different methods on it and see what's being removed. Is there a Lightkurve to combine multiple test sectors to study an object using sectors that may not be separated by a long gap? So Joyce, you're talking about, say, sector 31 and 32 or something like that. Is that correct?
Either case, I think. So it could be sector 1 and 12. Or
Right. So I actually have done, so the reason why I also know a bit more about my Lightkurve and know why it shouldn't be sloping like this is because I actually did the analysis for the sector 5 data as well. And so, yes, you can download the data for each one of these and apply the correction to each sector, but you need to apply the correction separately for each sector, because each sector is slightly different, because it's a spacecraft with lots of different things happening over time. And so the corrections would be slightly different, and your object's going to be on a different CCD, or even maybe in a different place on the CCD. So the shape of your pixel response function will be different. So yes, what I would do is download the data for each sector individually, apply the corrections and assess each sector separately, and then look at your data at the end. Can you please say again the PLD plot of 3 masks? What is the PLD aperture mask? So the PLD aperture mask that I applied specifically, so I actually didn't define one for the purpose of this tutorial. You can define one if you want to, in this correct part of the correct, you can basically say aperture mask equals, and then your Boolean that you defined earlier. In this case, I let it figure one out. And if you go to the PLD page on Lightkurve in the API, it tells you how it does that. And in this case, it shows you that the aperture mask it defined for my object was these 3 pixels here. And assuming that it used some sort of threshold sigma mask to define that. But again, you can input your own aperture mask, and you can also input your own background mask should you wish as well. For the very bright stars, I find doing simple background subtraction often returns a better light curve when I use regressor, which is less overfitting and less scatter. Does this seem absurd? There are more complex techniques. Jonathan, to be honest, I found the same thing. When I use regression correctors and design matrix, I actually have typically found better answers as well. Like I said, each one of these correctors can be tailored to different types of objects. I specifically am interested in supernovae, novae, all those sorts of things, and find that certain correctors do better than others. And yes, so you're not, no, this is you kind of tailor your correction based on your kind of objects, I think, and the brightness of the objects as well, and how crowded the objects might be. Okay, identifying real versus instrumental trends on the different methods. Which of them are only using info from surrounded pixels, and which, if any, are empirically fitting trends in the target pixels themselves, even if those aren't in the surroundings? So the ones that I've showed you which use pixels are only looking at background pixels and not using the target pixels. So it only uses the background pixels to determine the trends.
And that's true of the regression correctors as well. I wasn't sure if that was a regression on the data themselves or only on the background.
So in the regression corrector, let me bring this one up. So with the CBV one, that's slightly different, but with the regression correction and the PLD, they're both based on linear regression of the background information.
Thank you.
Okay. And yes, things do seem to be a lot like a case-by-case basis. I agree with that, Jonathan. It can be difficult. So for instance, when you're trying to look at crowding of things, so this is my introduction to crowding tutorial. Can you see this? Because I know I specified a specific screen. Can you see the understanding crowding screen that I've put up right now? If not, I might need to switch screens.
No, I can see.
Okay, perfect. Thank you very much. Mm-hmm. So in this case, I'm looking at an object, and I'm looking, this is the PLD SAP flux. So this is the one that's all been corrected. And then this is the SAP flux. And there's significant differences here between the PLD and SAP. And this is caused a lot in part by crowding effects, essentially. And so in the next tutorials, I have this discussion where I do this PLD correction, so to get rid of, scattered light, instrumental noise, etc. But then you also have to account for the fact that there's this crowding, and the reason being that you have your object, this is your object, and this is another object really close by. So obviously you're going to get, not only are you going to be missing some of the flux from your actual object of interest from this aperture, but you're also going to be getting some of the flux from this object in here. And now in our target pixel file, there are 2 parameters. These parameters are called, and again, you can look through this tutorial in your own time, but these parameters are called the crowd SAP and the FLRC SAP, and these can be used to apply those sorts of corrections if you have a very crowded field. Anything else? I hope I'm doing okay at answering these questions. I think that it is showing that, things are very much on a case-by-case basis.
If you're dealing with a target that's only in the FFIs, are you sort of on your own for figuring out the crowding correction?
See, so this is actually something that I'm currently working on, because again, a lot of my objects, the supernovae and things like that, are in the FFIs, and unless you've had that object be observed at the same time as a specific target, then yes, you're pretty much on your own in terms of figuring out crowding and things like that. But I'm trying to develop a little tool that will help that a little bit. So yes. So
I'll
what you
look forward to seeing it.
I know, me too. No, I've done part of it. What you would need to think about, I mean, I don't know how familiar people are with the TESS pixel response functions, but you'd need to look at things like that and like look at the other sources in your field and then try to figure out, you know, how much of the light, if you were doing a certain threshold pixel mask, how much of the light from your object would actually be contaminated by the other object based on the pixel response function. So I've already written a little corrector thing for if you have a target pixel file and you have those two parameters, but I'm working on something else for if you just have an FFI and you don't know those parameters.
Yeah, and if I can jump in, anyone, if you have ideas or requests for specific tutorials, I think they're very much welcome. And Rebecca's also been starting to pull together videos as well as notebooks and websites. So yeah, it's been great. Thank you, Rebecca. Should we wrap up? I do have one announcement before we close.
Yeah, I just want to say thank you, everybody, for your time today. I hope that you found this useful. I'm sorry if I went through things very quickly. For those of you that I couldn't answer your questions directly during this session, I will look into the questions and get back to you on them with more detail. Also, please feel free to post more remarks and questions on this Slack channel throughout the day. I will address each one individually. And yeah, if you have, like Nicole says, if you have any ideas for things or tools that you would like, I'm happy to listen and work with you on them. But otherwise, thank you very much for your time, everyone.
Yeah. And just a reminder, there is a talk on Juno at 11:45 East Coast time after the rest of the Splinter sessions wrap up. Thanks, everybody. This is great.
Thanks, everyone. Have a great day and enjoy the rest of the conference.
Thank you. Bye.
And Rebecca, don't forget to end the meeting for all.
Correct, I will.
Okay.
I'm just going to let everyone pick her off, and if there's any more questions, I can try and answer.
Yep, lots of thank yous in the Slack.
Yeah.
I tried to put a check mark next to all the questions that were answered.
I want to look into the error thing and try and figure that out a bit better.
And Michael put a Slack message as well.
Yeah, he did. Thank you very much, Michael.
Okay, I think we're done. I'm gonna
Thanks
sign off.
All right, take care.
Bye.
Good stuff.
Is that all right?
Yeah, good stuff.
Oh my goodness, what a day. I got some good questions. The audience is wonderful. Thank you guys who are still on here. It's a lot more interactive and a lot more questions, so I'm very happy about that.
All right, hopefully people will be emailing you.
I want emails. I want to work on more stuff. And I finally got the crowding corrector class working yesterday. It was written ages ago, but I need some help from Gert to figure out exactly how it should be put back in. But now it's all working, so I'm great.
All right, I'm going to hop off to something else, I guess.
All right, have a great day, Tom.
Bye. You too.